Hello everyone. So I hope you all can hear me. Okay, so please let me know if you encounter any technical issue that I'm not aware of. All right. So before we continue, maybe we can let me one moment. Okay. Before we continue, perhaps we can do a small recap for this chapter, which is image transformations first. Then later on, we will finish up the last part of this chapter, which is the DWT. Okay. So for this chapter, we are actually looking into image transformations. So the image transformation here is not, I think I repeat this several times. The image transformation here is not it's not the geometrical image transformation, whereby we are not concerning the, you know, how an object move from uh, within a specific location from location A to location B, something like that. Okay, but instead, this is to transform the entire domain, whereby transform from the spatial domain into other domain, for example, frequency domain. Okay, so this is regarding the transformation of the image domain. So in terms of image transformation, we have three different transformations, which is DFT, DCT, and DWT. Of course, this is not the only transformation we have in terms of frequency domain, but instead, these three are the fundamental that we will learn in for image processing. Okay, so the human eye is more sensitive towards this region, whereby you can observe a rising. I mean, the area under the curve is greater in such a region. Okay, which means it is region where human eye is sensitive, whereby human eye is much more sensitive towards um, medium contrast and also the medium frequency. Okay, but anyhow, actually, human eye is also can focus in this region and this region, but the sensitivity will be reduced lah. Okay, depends on different human eye capability. So this is the original spatial domain, and this is the frequency domain. So by transferring to the frequency domain, one's may not be able to understand the image by looking at it alone. Okay, so but we can actually I mean harvest many other different kind of information. For example, the information regarding to low frequency or the information regarding to high frequency, which is at the boundary of the uh, frequency domain. Okay, so later on we will, I mean, in Fourier transform, first of all, of course, we did not really uh, need the Fourier transform to perform calculations accordingly, but nonetheless, we need to understand how is, changing the vector, changing the phase, would affect the entire output. So in this field slide, we'll explain on the vector k, which include the frequency and also the directions and the phase, amplitude, and as well the what else? Okay, so these are the phase, these are the amplitude, and this is the vector k. So basically, in frequency domain like this one, so this is the k vector lah. Okay, depends which direction the character is, and also um how long the vector it is. For example, this one which means it is referring towards the high frequency information, and if the vector is very close, it is towards a specific directions, and also because it is very close to the origin, which means it is referring to the low frequency information. Okay, so this is Fourier. So by removing removing the high frequency information, so we still able to describe this image as Englishman maybe. And but when we remove the low frequency information and retain only the high frequency information, we can no longer tell what is this image. The meaning of this image. But instead, we can able to, we able to mine or harvest all the high frequency information. So if let's say you have, your image is corrupted by noises, of course, there are many different types of noise. So the most common one would be salt and pepper or Gaussians. So salt and pepper and Gaussians is those noise which is created by uh, sudden change in pixel intensity. So since sudden change in pixel intensity, this is considered part of the definitions for high frequency information. So that is why by masking out the low frequency information and removing the high frequency information, you can actually uh, remove the noise which is contribute towards the high frequency informations. Okay, but nonetheless, by removing all these high frequency information, you might the output image might be very blur and also lost your high contrast, the fine texture, all would be lost. Okay. So we have learned DFT, but in terms of image processing, we are actually using DCT and DWT. So DCT would be for JPEG compressions, and DWT will be using in JPEG 2000. Okay, JPEG 2000. So the 2000 is just to differentiate between the JPEG and JPEG 2000. Okay, JPEG would be the most common um, image compressions method we are using until now, and JPEG 2000 might be not so popular lah. Okay. So this is the, after DCT, you will get something like this one, and you will learn more regarding this DCT coefficient in next chapter, okay, which is chapter 6. So the first top left, this coefficient is known as DC coefficient, okay, and the rest is known as SC coefficient. So usually in one, 8 times 8, 8 times 8 pixel block, the DC value would be much more greater lah. Why? That is because in every images, especially uh, for those images which is from harvest from the natural environment, the low frequency information would be in higher proportions towards the high frequency information. That is why, of course, there are some exceptions. For example, the image is exactly full of noise, which is salt and pepper Gaussian noise. So you would expect the value over here is much more greater lah. Okay, but the value here would be smaller for those noisy image. But for most of the cases, because even though the noises are corrupted, the input image, it's not so possible that uh, maybe 80 to 90% of the pixels being corrupted. Sometimes maybe 10 to 20, already very severe. You might see obvious noise distribute all over the input image already. Okay, that is just for 10 to 20%. So it's not possible to have such an image that you have after the DCT, the value in this region is very high and this value is very low. It's not so possible. Okay, so that is the reason why, of course, most of the case, DC value will be greater than the rest of it, but you have to know reason why, okay, why it is greater. So this is the DCT coefficients chart. So this figure, the strip of white and black strip is actually referring to the sine wave, where this one is referring to white strip and this one is referring to black strip. Okay, so this is a flat image, and this is white and black, white, black, white, and so forth. Okay, so on and so forth. So after you joining both in X and Y direction, you will get a sort of checker box over here. Okay. So Okay, so that is all for DFT, DCT, and DWT. For DFT and DCT, DFT will be the most fundamental. Okay, that is why, because DCT and DWT are based on DFT as well. Sort of, improvement. Okay, it's not possible to have DCT and DWT without DFT. So the reason why we select DCT is that the computation method for DCT is much more simpler than DFT, because in DCT we did not involve the imaginary part. And for DWT, it is better than the DCT and DFT is that for DCT and DFT, after conversions to the frequency domain, you will lose all the spatial information in the spatial domain, which means you have one image and then you convert to full, this is spatial domain, this is frequency domain. So after you convert to the frequency domain, actually all this information will be lost, because you already convert your original data into data which is in another domain. Okay, but for DWT, both of these spatial domain and frequency domain information are still retained. So that is why the uh, performance of the DWT after the compression method, eventually after the compression method, is much more better than JPEG. Okay, so this is the reason why people are choosing DWT. Nonetheless, JPEG 2000 is not so common to the public. Okay, so but in terms of performance of the algorithm, JPEG 2000 would be better. So in the DFT and DCT, once we transform the image into frequency, we no longer have the spatial information. So which means all the spatial information, for example, the pixel intensity, the correlation between the center pixel and the pixel neighbor pixel would be lost. Okay. So the Fourier transform combine the filter bank technology address this weakness, which means spatial and frequency domain both still retain the information still retain. Okay, so in the DWT, we have we apply two different filter and we get four different outputs. The filter would be low pass and high pass. So we apply the low pass filter and high pass filter either in a horizontal direction or vertical direction, so that we get LL, HL, LH, and HH. Again, do not memorize the flow of this flow chart. This is not a flow chart, but block diagram. Okay, do not memorize this block diagram, because the it depends on you apply low pass or high pass filter on row or column first. Okay, if you apply on row, which means you will get horizontal approximation and horizontal detail. But if you are apply on vertical, so this one come first. Okay, this one come first, which means the vertical and vertical detail. Okay, so make sure you understand the flow, how it is being implemented. For example, if you apply low pass filter, which means all high frequency information will be filtered out, right? So you only have the low frequency information. So that is how you get the low frequency information, which is approximation, and depends on which direction. If it is in the horizontal direction, so you will get a vertical approximation and so on and so forth. Okay, so do not memorize everything from the text. So you have LL, LH, HL, and HH. So this is how actually the DWT being implemented. Because you can see here is the original image, but later on, after the original input image, you apply the filter and then you get different LL, LH, HL, and HH, and then later on from here you can rebuild, so-called rebuild lah. But actually this is not the original image lah, because uh, during the upsampling and subsampling, some of the original information might be lost. Okay, so that is why this would be very, 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 very similar, but not the exactly same image. Okay, so that is why it is an approximate image. So here are the code in MATLAB to perform DWT. If you wish to try, you can try out, which means you can also search for uh, internet DWT to space MATLAB. So always when you're using MATLAB, no matter for what purposes, as long as you want to try to get the information regarding the MATLAB core function, always can search online, put on the core function space MATLAB. Okay, this is the way we actually get that. Else, you can try in MATLAB software. You type, I think help bracket your. I'm not sure you do need bracket, but I think help DWT2 is work lah. Okay, you can try on it. But usually I don't try that because that will usually will cause the MATLAB hang. Okay, that is my experience. Maybe different RAM might perform different. Okay, so CS, CH, CV, and CD, which mean the proximity matrix, horizontal detail, vertical, diagonal detail. So X is your input matrix, which is an image, and the W name is the mother wavelet. Okay, depends on what mother wavelet you want. So, for example, Dobersis. So, um, this is actually the MATLAB code to explain how this is being, um, mm, how this is being, to create this image, to create this one. Okay, I'm not sure if I want to go through this one because sometimes to explain the algorithm is very difficult. And anyhow, I think this one is okay to be copy and paste. So I think it's best for you all to copy the code and put in the MATLAB and try it. Okay, this is the best way to learn programming and algorithm. Okay, nonetheless, I will explain a bit. So this is to actually get the first layer, which means because we have RGB image. So this is the first layer, second layer, and third layer. So this is first layer, second layer, and third layer. The symbol here is referring that you take all the x and all the y value, okay, in the first layer and second and third layer. So db2 will be the duplexes, okay. You can check in the MATLAB. So db2 is actually that you want to use duplexes as the mother wavelet. So later on you have this is just a variable that you can declare anything else. Okay, so xn is in double. In order to visualize it, we need to divide it xn by 255. So these are some of the syntax that you might encounter if you are using MATLAB to develop assignment, lab, or maybe FYP. Because in different how should I put it? In different because in my experience, most of the times I encounter difficulties in MATLAB is that, first of all, you don't know what core function to use else, but I seldom use core function because we are not allowed to last time. So the second thing is that the syntax issue. I want to develop something easy, to extract something else from this image, but most of the time the difficulties will be using the syntax. Because syntax without the correct syntax you will not be able to develop the algorithm. Okay, so in order double is the how should I say this characteristic, no, the type, yeah, type. Double is the type of the image, so you cannot really display double image. So in order for you to do that, you need to divide by 255 to get to display this image. So sometimes in MATLAB you might saw uint8 something like that. So all those are types of the image. So if you are wondering why the image cannot be displayed, sometimes you should check out the type of the image. Okay, perhaps there will be a lot of discussion in this online. Okay, so later on, this is to standardize this line. Is actually we use to standardize the function better visualize the output image. Just to rearrange. I believe in your assignment I did ask you all to plot the subplotted image, right? Subplot is actually a very common method to control the display of the uh, figure in a specific image. So subplot, which means something like this one. Okay, which means in one figure, you can actually subplot image A, B, C, D, E, F. Okay, Depends on the questions. So if you, and maybe you can put in the caption accordingly, the caption or caption accordingly, depends on the requirement of the question. So if the question asks you all to subplot in such a manner and you guys did not subplot in such a manner, so marks will not be given. Okay. So please make sure if the question asks, I think in assignment, if the question asks you all to subplot this and that, make sure you follow the instruction. Else, if you screenshot all the images one by one and put in the layout is different. Okay, so no marks will be given for subplot that questions. Okay, so later on, this is just to show the title. So this is how you get lah. So this is the input image, XA. XA, what is XA? What? Let me check. XA is the approximation of the input image. Yeah, approximation of the input image, which means in both the directions. Which means when the questions use the word approximation, which means this is low frequency information. Okay, so which means this is the approximation in X and Y direction. So this is the horizontal detail. This is the vertical detail. So as I said, usually because horizontal details is always referring to high frequency information. High frequency information. So most of the time, the high frequency information is not readily to be understand by human eye. So that is why in approximation image, you still able to understand, oh, this is an image, with different kind of pebbles and garlic showing in the figure. But this one is hardly for you to tell. Okay, so this is in horizontal, this is in vertical direction, and this is in diagonal. Again, the details in diagonal, again, is not so ready to be described by human eye. Okay, so first layer comparison, you have horizontal, vertical, and also diagonal. And this is for the approximation of the image after subsampling. And this is a horizontal detail. Again, details, so it's hardly for you to see what it is. And for these approximations of image, because this is the second layer of approximation, so that is why when you compare this XAA and XA, you will find that the XAA is, you're still able to see something inside. Maybe it's hardly to guess also if you don't know what is the input image. But nonetheless, it's still better than this one, right? So, but I mean, why it is being, the contrast, the sharpness is being highly degraded is that you only extract the approximate information from this one. So that is why it is, um, more is blurrer than the before the XA lah. Okay, so you have input and then approximation which is in XA, another approximation which is in XAA. So XAA is built based on XA. Okay, and XA is built based on input. So that is why here you will find that, oh, this image is quite blurred. And again, the horizontal detail is very I mean, cannot be understand. Same to vertical and diagonal. So this is a second layer, horizontal, vertical, and diagonal image. And when you compare, you just actually the display on, I mean, using this method to display is not a must. But why people, I mean, why this figure subplot in such a manner is that you have first layer of uh first layer of horizontal low pass filter, first layer of low pass filter using horizontal, and first layer of diagonal. Okay. Sorry, this is a high pass followed by low pass. This is low pass followed by high pass. High followed by low. This is low followed by high. This is diagonal because high and high. And this one would be your approximation image. So based on the approximation image, and then later on develop into four different, which is LL, HL, LH, and HH. So that is why this image plot in such a way, because you cannot develop the approximation image using this one and this one. Okay, you cannot build an image using I mean to get the approximation using HL, HLH, and HH. So that is why you can only build the image based on LL. So from this LL, you build the second layer, which is another LL. LH, HH, and HL. Okay, so that is why the image, put in such a way. So DWT is the heart of the JPEG 2000 image compression standard, where much better compression ratio, image quality, and other features can be obtained compared to the DCT-based JPEG compression standard. The technical mathematical details of this DWT, however, is out of the scope of this course, which means you don't need to learn, the exact flow of DWT lah. But of course, DCT you have to learn. Okay, DCT is under the slippers, which is next chapter. So just a fast recap. So we learned DFT, DCT, and DWT. And for DFT, it is the basic of Fourier transform, but actually we are using this in terms of converting the spatial into frequency domain. So that is the basic of DFT lah. So after that DFT, we have using DCT, which is the cosine wave. So in DCT, basically everything is same as the DFT, just that in DCT we have uh, uh, simpler calculations such that we don't use the imaginary part lah. So when the calculation involves imaginary part, it is always time consuming. But the DCT did not involve the imaginary part, so with that it is easier to compute. And then later on, and DCT is the heart of JPEG to JPEG. Okay, and in JPEG 2000, I mean in DWT, we have the wavelet transform. Wavelet transform we is better than DCT and DFT. Why? That is because in DCT and DFT, we will lose all the spatial domain information when we convert from spatial into frequency domain. But in DWT, we have both of these information. So that is why DWT will be better. And DWT is the heart of JPEG 2000. But nonetheless, in the next chapter, which is image compression, we will learn about DCT only. Okay, because the DWT is not within the scope of this course. Okay, so any questions so far regarding the image transformations? Any questions? None. Okay, so if none, then we continue to next chapter, which is the image compression. So as we learn in, I mean, as we learn in chapter one, in terms of multimedia, I mean, in terms of MTAA, the entire subject or the another course for this subject is that uh, we have to know what is the basic in multimedia. So basic in multimedia would be 5 elements, right? Text, image, audio, animations, and video. So all these 5 elements, we will be focused in image. Text is very common, and we did not really process text. Why? The reason why we did not process text is that text is already, did not occupy many spaces. So, and also the size is very, very less. So it's not worth the time to process the text. Eventually, we process the text, it is in terms of image processing, which means we capture the image of the text and then we convert the text, the text in the image into a text. Okay, um, this is quite I think back to 5 to 10 years back. This is image processing application in terms of documentation is quite mainstream, I would say. Okay, even eventually nowadays, I think iPad did have this uh, pictures where you capture the image and then it will automatically convert all the text within the image into text lah. Okay, but nonetheless, the accuracy is high or low, still pending for debate. So, but I think most of the mobile or high technology uh, device is equipped with this technology already. Okay, so that is part of it. And also when we talk about multimedia, we always concern about the storage, because a very HD uh, movie can take up to 5 gig. But of course, I think nowadays less people using. I mean, in the general public, quite less to download something else. Perhaps you all watch or maybe listen sort of the music, Spotify, something like that. So you don't need to download. But who would be the one who concern the size of the multimedia? Those would be Amazon. What else? Amazon, the library of, because Amazon is actually, actually when we are using cloud, Apple, Amazon, all these people, they are actually managing the storage. Okay. Actually, oh, I don't need to use my storage because the storage is less is fine. I use cloud, and you are actually purchasing the cloud, right? So eventually, maybe Apple or whoever give you the storage in the cloud or the virtual spaces, eventually they are managing the storage size. So that is why sometimes when you upload something to the cloud, um, it may cause a different change of size. Of course, the change of size wouldn't really affect your quality of image or quality of audio lah. Okay, but actually there are several methods to store things to the cloud. Of course, that is not the interest of the general public lah. General public just drag and put it in there or just register an account, that's all. But actually Amazon is a typical example for storage. Because previously, uh, my previous experience, I did develop an algorithm called Amazon S3. I forgot what is it. S3 simple 3S. Okay. Amazon S3 is a storing protocol for Amazon. So Amazon, you can actually imagine Amazon is a big data. Amazon did have a big computer, and then all the data within this world is being stored into it. So perhaps we don't think storage is a big concern to us, but for Amazon, Apple, Google, all these big companies, they are dealing with this every day. Okay, so that is why compression is a very concern for them. Okay, so of course, if you have part of this skill, they might interested to take up you lah. Okay, so image, we will learn compression is not only in image, but we will learn in audio and video as well. But the way we compress image and video should be more or less lah. But of course, there would be a bit different because nonetheless, at the end of the day, the video is actually arranging different images in a series of time. So we are actually end up the video is actually part of the image as well. So that is why most of the algorithm applicable to image is applicable to video as well. But there would be something different there, such that to process the image in real time, the video in real time, because the video is changing, right? Many different frames in 1 second. So that would be a bit different over there. So the rest would be audio. Audio processing will be a bit different, but nonetheless, we are trying to explore the limitation of human being. So I hope you all still can recall, this is the contrast, this is the frequency. So human eye is not so sensitive towards um, low contrast and high frequency information, which is at this portion, or the low frequency information and it is low contrast as well. So this part is not so sensitive towards human eye. So that is why during the image compression method, we are trying to throw away or trying to omit all the information in this region. Okay, so that is why it's very important for us to use DCT because we want to convert to low and high frequency and remain the low frequency and remove the remain the low frequency information and omit part of the high frequency information. We will not omit all the high frequency information because we just need to reduce the size of the multimedia, but we don't want to, we have to balance the trade-off, the quality of the image and also the size of the storage or the size of the multimedia itself. Okay, so in image compressions, we are actually learning the method to perform these, okay, image compression. So we would actually learn I mean, we would learn what is lossless and what is lossy. Lossless, which means without loss any data, we call it as lossless. And lossy, which means at the end of the day, you won't be able to recover the information. So that is called lossy. Okay. For lossless, because compression, we have two different compression. One of the compression we can recover back the missing information. For example, this is a string, and then lossless is like you compress it, so the space taken, the length would be reduced. For example, 10 cm become 5 cm. But if it is a lossy, which means after that you actually cut it off, you know, become 5 cm. But the rest of it already being cut out, permanently removed. So that is why you cannot recover back to this one. But for the first case, you can actually remove both the wooden block, then you can convert back to the original one. Okay, so this is the lossless and lossy image compression. And we have JPEG, which is using DCT, and JPEG 2000, which is using DWT. Okay, so multimedia data is usually big in size, especially for image and also the video and audio. Text usually very small. Okay. Uh, of course, the image is not those image like selfie or the images you snap using your DSLR. But uh, usually we are referring to those images with a specific, we require very, very high definition. Because very high definition, which means you require more data to be included in your image. For example, MRI, for example, CT, for example, X-ray. All those are all those are considered as high definition information uh, images. So, and also the histopathology images. Histopathology is something, I wouldn't say new because it's been using in UK and US quite a number of years, maybe 1 decades or 2 decades already. But now in Malaysia, we are start using this maybe many years ago but less than 10 years I think. But the maturity of histopathology image is still uh, not so common yet because the scanner to scan the histopathology image is very, very expensive. Okay, so basically last time when we are talking about the form 5, we slice the onion and put the onion tissue on a glass slide, right? And then you put the another slide on top of it, put in the stain, maybe iodine or whatsoever, and then you put in under a light microscope to to look into the cells of the onion and etc. Right? So this is so-called a slide, like glass slide. But for histopathology, it is actually put this glass slide into sort of scanner, maybe something like this one. The scanner is actually look like your printer. You put the slide into this scanner, and then from this scanner, it will scan the entire slide and produce one image. And this image is very big, sometimes up to 5 GB for one image only. One image for 5 GB. But later on, you can scale up this image up to 40x, 30x, 10x, and so on and so forth. Okay, so that is why all this kind of this one image is only one small tissue only. So if you, let's say you want to do a sampling, maybe 10 or 20, then 10 or 20 might multiply by 5 GB lah. Okay, so that is why usually the images in medical field is very, very big. And this is also true when we require uh, more and more, I mean, better quality information. So for example, I want to send a video, then the video, for example, in WhatsApp or WeChat, sometimes the image captured by your mobile phone is the quality is different from the images that you capture using WhatsApp. Okay, because they tend to compress the image before sending out the image. So that is why the image that you send, I mean, you capture using the WhatsApp apps or the WeChat or the Line, the quality will be a bit different rather than when you compare to the image that you capture using a mobile phone and then send via these apps. Okay. So typically, radiograph scan at 7 micro resolutions, 70 micro resolution size of 1 pixel is equivalent to this lah. With a bit depth of 12 bits per pixel will cause the pixel size of the image up to few MB lah. Okay, and don't forget this is not only one. You maybe up to for 1 month maybe up to millions of uh, a radiograph. Okay, because especially for a general hospital, you know why general hospital is very busy is that many people come and seek doctor from the entire region is coming to the general hospital for so that is why the data storage in radiograph is very very important. And nowadays everything is going online or digitized. So this would cause a lot of issue lah, because last time we don't have, we the last time we retain everything using the manual, for example manual x-ray, manual this and that, but later on we all convert to online, everything become a very big storage. Okay, eventually last time I mean before the MCO lah, Google did not charge for storage. If you buy the Google Suite, it did not charge for any storage. But now, I think end of this year, starting from next year January, Google start to charge for 1 TB, I think. Sorry, 100 TB. If you brought the Google account, Google Suite or something like that. So one account up to 100 TB for under one subscription. If you need more than 100 TB, they need to charge you more, something like that. So that is why compression is anyhow a big issue lah. Okay. So CD quality audio with sampling the rate of 44.1 kilohertz, 16 bit per sample stereo generate data at a rate of 176.4 kb per second, kilobyte per second. So these are the, let me see what is this. This is just a table to show you, 1 bit is actually how many byte and so on and so forth. Okay, so I think you already know this since the first chapter lah. Okay, because you need to perform the calculation, right? Divide by 8 and then divide by 1024 and so on. So these are the typical, of course this is depends on the size of the image because not all size remain same as this one. So MRI would be 131 kb and so on. Okay. We have a limited network bandwidth. So this is another reason why we want to do compression. I believe both of these reasons already being explained in chapter 1 because we have limited storage and also we have limited network bandwidth. I think storage we can still can capable to handle, but then in terms of bandwidth, it's sometimes very difficult. You know, when you want to send a video to some other people and the video is keep on loading, like load for forever and never send out. That is because we have a very limited bandwidth in Malaysia, uh, especially. So that is why it's very difficult for you to send a big image or big uh, or big file, even if eventually via email. I think email is kept at 10 MB, I think. So if you want to send your thesis, which have many images inside the thesis, perhaps you cannot send via email alone. Maybe you need to upload the drive and then send the link instead. Okay, so that is the limitation over there. Because if you have a email sending over with a big file, it's very difficult for the bandwidth to handle your sending. Okay, your connection over there. So image sending path, this data uncompressed through the limited network this would be the speed lah. Okay. So these are Ethernet, LAN, ADSL, SDN, and V90 modem. So we have limited storage space, which is the, I think you all might not know this one. This is the device we used last time. I think sometime now we still using lah. But usually I think now we use more on the Wi-Fi modem lah. Okay, we seldom to use LAN cable. So compression allow large size medium such as audio, video, image to be effectively store and transmit. So store and transmit, store is will be referring to storage, and transmission would be referring to bandwidth. So better quality signal to be transmitted through network of limited bandwidth, faster transmission of data, and reduce storage requirement of multimedia data, support multimedia intensive application such as video conference, digital library, and telemedicine. So factor that would increase the media size would be increasing resolution, sampling rate, and more bits per pixel to represent more color. So for this one, resolution, for example, you have a higher resolution, which means you have higher number of pixels. Higher number of pixels, which means you have higher, the pixel need to hold more information in one bit. Like, for example, you have a grayscale color, so you have 8 bit, right? So if you are using RGB, so you have 24 bit. So which means each bit is holding more and more data. So this is for 1 and 2. And sampling rate will be applicable for video and audio. In image, not really, because image is a discrete or time independent multimedia. So that is why sampling rate always involves time taken. Okay, which means I want to take the sample how many times per second for how many seconds. For example, you have a wave like this one. Okay, so if let's say I only this is second, I only take 4 sample, so divide by 4. So which means after plotting, I would have 1, 2, 3, and 4. So this would be my point. 1, 2, 3, 4. So basically, this is the point I have after I get 4 sampling. Okay, and the sampling data rate must be same across a period of time. For example, 1 second. Then within 1 second, I will take 4 sample in 1 second, and the time interval of this 4 second would be the same. Okay, so this is how I get the data. But nonetheless, this data when we compare to original one is like not really the same. Okay, if let's say I only take one sampling in 1 second, so which means my point is something like this one. So when compare this and the original one is totally different. So let's say I have 100 or up to million sampling. So which means when the graph is something like this, so I will take a lot of different sampling. So after that, after the sampling, and after I connect all these points, it is very, very likely to the original data. Okay, so that is why the higher the sampling rate, the better the representation of the data. Okay, for this sampling rate, we will learn in audio processing especially. And let me think. Yeah, I think audio processing especially. So this is very important in terms of mining the data. Okay, we have Nyquist theorem. I think I mentioned before Nyquist theorem, which uh, specifically to address this issue, address the issue of sampling data rate. Okay, so factor the aforementioned help to improve the immediate quality at the expense of increased media size. So which means you have a better quality, but of course with an increase in medium size. Principle of data compression. The terms of data compression is equivalent to source coding or bit rate reduction. Actually, the compression here is to actually nothing for you to compress. A mouse requires this space, and that all it is. You cannot, press it, squeeze it to make it smaller. No, not something like that. But instead, we try to remove some part of the mouse, which is not so useful to us. Okay, for example, you have a bottle like this one. Sorry, I should draw it. For example, you have a machine part like this one. Nonetheless, at the end of the day, you still need to, this is the original size. Okay, and you cannot, put in force from both sides to make the machine, compress out to occupy a smaller space, because this will eventually damage all the information or all the data within this machine. So what we can do is that we remove some part of the machine which is not so useful as compared to the others. For example, oh, this part is not so useful, so I remove this, not useful, remove. So later on, maybe we have a smaller space. Oh, so we have a smaller space machine. So this is how we actually perform the compression. The same thing apply in image processing. We are not going to suppress or squeeze any of the pixel, but instead we would try to identify if this pixel important to human or important to user. If this pixel is not so important to user, so we directly remove this pixel. So this is how we do the compression. For example, you have a high you have a image convert to frequency domain. So this is your origin. This would be the high frequency data. So if let's say, okay, this high frequency data is not so important, so perhaps I will remove the rest. All the high frequency data in this region will be removed. So later on, you would retain all the information, but with a smaller size. But of course, you sacrifice high frequency information here. This is how the compression being performed. Okay, you are not going to, compress one bit so that one bit no longer hold. For example, it is RGB lah. Of course, it will hold R, G, and B layer information, right? You are not going to remove any of the layer, but instead, from all these three layers, we try to identify which pixel is not so contributive to the entire image. So you remove that one. Okay, so definition of data compression, the process by which information is encoded using fewer bit or other unit which bear information that are more obvious representation would use. The process by which the data is converted from one format to another format, which is physically smaller in size. And some logical information is stored using physical information, using less physical information. The process of conversion of data specific scheme for encoding the information. So basically, everything deal with computer. You are actually dealing with the big code lah, which means 0 1 0 1 0 0 all those. But actually, we are not going to that level yet, because that one will be very computer science based lah. Okay. Nonetheless, you have to know what is happening there when we perform the JPEG compression. So compression is a coding process that produces the total number of bits to represent similar information. To achieve compression, the original symbol in the message are recorded with code words that result in lesser number of bits. When you remove the number of bits, reduce the number of bits, the size will be reduced, because each bit hold a specific size. So when the bit being some bit being removed, so of course your size will be reduced. And code performance compression and decode performance decompressions. So this is the general scheme for that, encoder, which is compression, storage, and then decode. But of course, this is for lossless only lah. For lossy one, you are not able to recover or decompress. That is not possible for you to decompress. Compression and decompression techniques are utilized for a number of applications, particularly on printed system, document storage, video conferencing, and etc. During the process of compression, redundancy information. Of course, not all, because based on the theory, most of the time the redundancy would be from high frequency information. It's very rare that a low frequency information would contribute to redundancy. Okay, so usually high information would be removed, resulting image being less number of bits. And when the image is being removed, not all, but part of the high frequency information being removed, you might result in an image which is a bit blur. Okay, the primary criterion is that the removal of the real information should not perceptible affect the quality of the result, which means eventually after your conversion, you still able to achieve the minimum criteria. For example, this is a picture with an apple. So after removing the high frequency information, you would still expect you can read, oh, this is an apple. Okay, it's impossible that, oh, after compression, oh, this is an orange. Not possible. Okay. So image compression technique may be classified as a lossless or lucid. So compression ratio is actually very simple. Basically, to divide the uncompressed with the compressed, that is how you actually, like I have I have 200 miles, and then later on discount by 10%. How many the miles is being discount? All sort of this question. Okay, so the compression ratio is used to measure the ratio of the data of size of the original data before compressed when compared to the data after being compressed. So basically, this is the um, simple ratio to calculate the ratio, 10 to 1, 5 to 1. So this is how being calculated. In MATLAB, you can use push WOS fit to fix the data and check the storage size of a particular image. So let A original uncompressed file, B become the compressed file size. So case A, uncompressed size is smaller than compressed size, which means the compression ratio is greater than 1. Smaller than 1. This one. For case 2, uncompressed size greater than the compressed size, which means the compression ratio is more greater than 1, which means the file is being compressed. For the case 1, actually, you are not compressing it, but then instead you are expanding the size. So if the compression ratio is less than 1.0, which means your compression representative will take more space than the original one. No compression occur. So which means uh, for case 1, it is not you are not compressing anything, but instead you're expanding the file size. Okay, so an original file with 123 megabyte is compressed with a compression ratio of 3:2. Determine the file size after the compression and how many percent that the storage space can be saved from the compression. So do the simple mathematics just using this one. Okay. Even though not using this equation, I wouldn't call it as an equation. I think this is more to the common sense. You know, discount after discount, you don't need a formula to do so. Just try to do the simple calculation. Okay. So this one simply just to calculate the ratio. So compression ratio will be uncompressed divided by compressed. So since it is 3:2, so this would be the equation. After you write down this equation, you just solve using a simple mathematics. So you will get 2 megabytes. So the compression ratio 1 minus this one, just put in the output here and then divide by 11233, which is the original uh, size. Then you will get 33.33%. Okay. So this is how you get this one. Anyhow, this is for your information. Okay. Example 2, if the compressed file obtained in example 1 is used as the original image for decompress with the compression ratio of 1 to 5, determine the file size after the decompress. So now using this one and to decompress, basically just to revert it. Okay, so this is it. Just simply, of course, first of all, you need to write out these equations. If you can write out this one, so basically no issue. But nonetheless, in case sort of this question appear, please prepare. Please write down all the solutions. Don't just give me 410 MB lah. Okay. Mm. So the song on a CD are uncompressed. Oh, this one is 410. Basically, this is the equations. So just solve it and get the uncompressed sign. That's all. The song on a CD are uncompressed with a data rate of 16 bit per sample or channel times 2. Da, 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 da. Okay, this is to tell what. Okay, we skip this slide. I have no idea why this slide is here. Okay, okay, we continue. The next slide. This is the original image. I mean A, B, and C. As you can see, when you look into B compared with A or C compared with A, of course, when you compare C with A, it will be very, very obvious. Not only that the pixel is, the entire quality of the image is being decreased, and also you would aware that the there is a blocky field over there. You know, in this one, there will be a blocky field, and the blocky field, can you see all this block field? You know, all this block. These are the blocky field that I mentioned previously, and same to this one. Okay, so as you can see, all these blocky field, all these blocks would be very similar to cosine wave. You know, all those 84 blocks in the cosine, uh, you know, the white color and black color strip, all those checkerbox will be very similar. That is because it is actually checking all these specifically these 8 times 8 block, which one contribute more to this one. So they will assign the value over there. So that is how, but in when you look into this, that might be very, this is a black and white strip and etc. But when we look into the whole image, the image in a whole, you're still able to understand this is a lady lah. Okay, but for this one, most of the block, especially this one, you still able, when you zoom out, you still able to see this is eye lah. Okay, but when you zoom in, you will found that they are the blocks is very obvious now. And some of the block is a flat image, which means nothing changes over there lah. Okay. So that is that is the reason why you have a blocky field, because in DCT we are actually processing the compressed algorithm using 8 times 8 or 16 times 16. Usually we perform using 8 times 8. Okay, so that is why you would see a blocky field in your output image when the compression rate is very high. Okay, so example of JPEG distortion. Image A shows the original image, while image B and C show the restore image using compression ratio 10 to 1 and 45 to 1. So respectively, the high compression ratio used in C result in an 8 times 8 pixel block being represented by less than 12 bits. Okay. So lossy versus lossless versus lossy data compression. Data compression can be classified into lossless and lossy. So lossless, which means no loss of image information, and lossy, which means loss many image information. A lossless method allows exact reconstruction. This is the main difference because in lossless and lossy both are compressed image, but in lossless you can allow reconstruction, but in lossy you are not allowed. Okay, of all the individual pixels where a lossy method does not. So lossless method often refer to an image coding rather than compressions, with much of the original development being directed towards the transmission of image from a space props. So in lossless compression algorithm, the aim to reduce the amount of source information to be transmitted in such a way that when the compressed information is decompressed, there is no alterations or loss of information. So this is the main uh, different, in image compression, you only have lossless and lossy, and lossy would be both perform the image conversion accordingly. Just that lossless, you can reconstruct the original input image, but the lossy you cannot, because for lossy, the image being omitted will be permanently omitted. Okay. In other words, the decompressed file is an exact copy of the file before compressed. Lossless compression is reversible. Since this is actually lossless and lossy is describing the algorithm lah, not the image itself. Perhaps to some extent sounds similar, but actually lossless and lossy is describing the algorithm who perform the image compression, but not the, oh, this is a lossless image, not something like that. JPEG is a lossy image, it's true, but we do not use it something, we do not describe the image as lossy or lossless, because image is an image. But the algorithm could be lossy and could be lossless. Okay, so lossy and lossless is to describe the compression algorithm, not the output image. Okay, so it is used in the compressions of data or of text, data, and medical image. Example, lossless compression would be WinZip, uh, zip file format, and lossless JPEG. Okay, so of course, JPEG there would be different extension. Different algorithm in terms of JPEG lah. So you have lossless JPEG, you have JPEG 2000, you have JPEG. Okay, and the GIF graphical interchange file is a format used on the web that provide lossless compression. So this is the protocol that we use online. For online graphics, usually it would be in GIF format. Since the original data can be obtained back exactly, the compression ratio is smaller, and when compared to lossy compression. And this is the main, also another main difference between lossy and lossless is that lossless can reconstruct the original image. Lossy cannot. But lossless cannot compress the image at a very, very high compression factor. For example, 10 to 1, lossless cannot, but lossy can. More than that also can, 45 to 1 also can. Because they are just, cutting off an edge from the for the cake, for your cake, you're cutting off part of it. But in lossless, it is not something like that. Okay, so whatever you cut off, you have to reconstruct it and get the original input. So that is the difference between lossless and lossy. It's not possible for the lossless algorithm to perform higher compression, but then how do you store the data being compressed and then later on recover back? So that is the trade-off over there. Okay, if you want to perform a very high degree of compressions, that must be a lossy compression. If you want to perform just maybe 10%, then lossless compression. That is because the lossless compression allow you to reconstruct back. But of course, if you think that the loss of high frequency information is okay for me, then you can go for lossy, because the processing rate of lossy would be faster than lossless. Okay. So lossless compression can achieve reductions in the size approximately 2 to 1 to 10 to 1 and the original size without visible affecting the image quality. So nonetheless, if you perform higher than that, 10 to 1, it will still affect the quality of the original input image. Lossless data compression algorithm, for example, run length encoding, Huffman coding, arithmetic coding, and Lampel-Zipf compressions usually exploit statistical redundancy to represent data without losing any information. So all these are example of the algorithm. Run length, Huffman, arithmetic, and Lampel-Zipf. We did not really learn this one as well, but we did learn run length and Huffman. Okay. Most common RLE run length encoding is the simplest lossless compressions algorithm, but far from the most effective. Again, this is, RLE is a very common method to be used, but it is not the best method to be used. Okay, same like the JPEG, it is a very common image extension to be used, but it is not the best image uh, extension to be used in terms of compressions and all those trade-offs. So lossy compression is a compression scheme that results in a significant loss of information when the data is compressed and decompressed. That is because the data cannot be recovered. So when you compress it and you wish to decompress it, basically nothing to be decompressed. Okay. It also known as perceptual coding. Original data cannot be obtained exactly as lossy compression and reduce the file size by permanently eliminating certain information, especially redundant information. So data loss is not significant perceptually. Humans hardly notice the difference. When the word perceptually being used is that I think this is nothing wrong, but actually it's very wrong. Something like that. Okay, I think the quality is still okay, but actually most of the image information already being removed. So that is called perceptually. I think that is called perceptually. Okay, so it is not from statistically. So that would be the difference. As I mentioned, as I used to mention, for example, this is an example. After remove the high frequency information, you still able to not all the high frequency information, but part of the high frequency information, you're still able to say, oh, this is an apple, nothing wrong with this image. Perhaps maybe a bit blur, but that is called perception. But in terms of we look back into the information provided by the original input image and the information after the removal of high frequency information, you will find that actually a lot of the original input image already, a lot of the information in the input image already lost. Okay, so that is called perception and also statistically. Human hardly notice the difference. Why human hardly notice the difference is that human are more sensitive towards this region. Okay, let's say you remove all the information here or most of the information beyond the curve. It would be shows, in terms of data analysis, you will find that, oh, many data already being removed. But in terms of human eye, it's like nothing much, something like that. Okay, so that would be the difference. Because at the end of the day, the image is meant for human to see, to enjoy, right? Okay, but of course, this is still depends on the application. If let's say I want to do something, for example, in terms of medical image, especially medical image, because medical image you need to use deep learning model and whatsoever model to segment the tumor, segment the cancer cell. So the pixel information, the all those information encrypted in the image is very crucial. Okay, but maybe sometimes human cannot see that. Oh, this is what I want, but in terms of the eye of the machine learning language, so it is very important to perform a specific algorithm. Okay, so that is the difference in terms of the applications. If you know just snap an image just to enjoy the image, so basically the high definition information is not so important. Okay, um, it is generally used for video and sound where a certain amount of image information loss will not be detected by user. So this is actually the main fundamental that we are performing any compressions in terms of multimedia, because in image we always explore the limitation of human being, and in the audio processing is the same. For example, when you went to a disco and then the music is very very loud, or maybe you go for a concert, the music is very very loud, and then after you exit from the stadium, perhaps you no longer can listen to your friend whisper to you, because the music is too loud just now, maybe just 5 minutes ago, and your a friend whispering to you something like that, you cannot listen. Maybe he or she need to speak louder so that you can listen what he is speaking at that moment, something like that. So that is the perception here. So in audio processing, we actually have sort of this kind of method, whereby when you have a great noise, and then we remove all the information here. That is because eventually you will have input signal here, but the signal is lower than the threshold. You will not able to listen this threshold, this signal. So that is how we perform the compressions in terms of audio. Okay, so we are still exploring the limitation of human, no matter in terms of ear or in terms of eye. Okay, so that is how that this would be. Although this sentence looks like very normal, but this is the fundamental how we actually apply the compressions in both audio and image and also video. Okay, example of lossy compression in image are JPEG 2000 for image compression. So we will learn, this is for DCT and this is for DWT. We will learn this in, the core. Okay, JPEG 2000 can be lossy and lossless algorithm dependence. So example of lossy compression would be in video would be MPEG 1, MPEG 2, and MPEG 4. And compression rate is higher which is typically 10 to 1 when compared to lossless compression. So technique, DCT block transform, wavelet transform, and vector quantizations. This one we will explain later on in this chapter as well. So data compression, you have lossless and lossy. Basically, these are the example. Okay. And again, JPEG 2000 can be both lossy and lossless. So be aware of the questions. Characteristic of lossless and lossless compressions and lossy compression. So no loss of information can be applied to any input data, and small compression rate. Compress ratio is very dependent on the input data. So this would be one of the characteristics of lossy, which means it is not able to handle high compression rate. But for lossless, loss of data and high compression ratio. So when you look into the image, when you compare both of it, you will find that lossless not that blur but lossy, you always for lossy compression, you always, when the compression rate is up to 10 or maybe beyond 10 to 1 ratio, you will always found a blocky field in the input image. Okay. Okay, later on we will start JPEG compression. Before that, we take 5, and then we start off the JPEG compression. Um, JPEG compression is very important. Okay, so do away. We take 5, and then we continue back JPEG compression. Before we start the JPEG compression, any questions? Any question regarding the previous slide? I think, yeah. So basically, to recap just now what we have learned, actually we just learned about lossy and lossless, uh, how, why the importance of image compression. I would say the previous slide is the sort of introductions. I mean, why it is crucial to perform image compressions and what types of compression we have and the extension. Okay, so basically we have lossy and lossless. Lossless is that we can convert back, we can reconstruct the compressed information, and lossless usually the compression scale will be smaller. Okay, and for lossy, the compression scale will be greater, maybe 45 to 1, 10 to 1, 15 to 1. But the uh, data being compressed or being omitted would be permanent. Okay, which means you cannot construct or recover back the missing data. Okay, that would be the main difference. And uh, for multimedia system, not only for image not applicable to image alone, we are actually the reason why you want to perform compression is that we have limited storage and limited bandwidth. Okay, we always concerned to sending data from one party to another party. So that is very important for us to have a, the size of the image or size of the data is comply or can be accommodated by the current bandwidth. So that is why uh, getting 5G is very important. And eventually now they are start to discuss on 6G already. So because for us, we are only, actually that is, this this has to be concerned that which area uh, the country is concerned on. For example, for example, normal students might be only concerned that to upload the image, to upload the assignment, and etc. So that would be the biggest issue when you cannot upload your assignment when the due date is there. That would be the concern. But for in terms of country, the military, and etc., the sending of data informations from this point to another point is very, very crucial. Because last time we don't have any data communication, don't have any handphone, cell phone, and etc. So the soldier is actually uh, you know the the minister is actually writing down, or the commander is actually writing down the notes on a paper and bring back these notes by a soldier from one location to another location. So if let's say the soldier die in the halfway, so which means the notes is not being delivered, and this may trigger war between countries. I believe we have several movie inspired by something like this already. So this is why 5G and 6G is very important. And last time during uh, actually there are several. If you did watch the all those movie regarding the war, you would be know for example Turing. Turing is a very famous mathematician where he actually uh, uncrypt the enigma. So it is enigma is the not the character in your Dota, but enigma is the machine that code the algorithms to encrypt all the secret information and etc. So that machine called an enigma. So and the Turing is the one who decode it lah. Okay, so these are actually I mean, all those are in old glory time, but now we are talking about 5G and 6G. So that is why different country wish to get this technology. If you have this technology, you would have better advantage in terms of military and in terms of telemedicine and etc. Of course, uh, when the layer is going down and down, we would be concerned like how many what is the speed for me to download and upload the movie and etc. But in terms of military, they have many uh, information can be sent with a better or a greater or a wider bandwidth. So you can send better information in, just one or within a second. So that is why the compression, the multimedia uh, are concerning about the bandwidth, are concerning about the storage and etc. Okay. So without further ado, we look into the JPEG compression. But I think today I will give you all a recap. I mean, some introductions in terms of JPEG compressions only. We will try to explain again next week, not next week, this Thursday. Okay. So JPEG compressions in 1992, JPEG become an international standard for compressing the digital still image. So over 80% of the image that are transmitted via the internet are stored using the JPEG standard. I believe not only the image transfer via the internet lah. Even within ourselves, we are using JPEG compression or JPEG as well. So JPEG is actually referring to Joint Photographer Expert Group. Standard is most widely known as lossy compression for continuous tone or grayscale or full color digital of a nature scene. So usually JPEG is meant for images that is captured from a nature scene. If you are a synthetic image or an image being removed the background, usually it will automatically appear as PNG. Okay, so that is by default lah. When you save, when you just type in the Google, say that a remove background, and then you put an image inside, and then the image is JPEG lah. You put the image inside, and then after remove the background, you download the image. It will be automatic appear as PNG. Of course, you can try to convert it to JPEG, but sometimes you're converting the image, especially those that are already being removed background. You convert to JPEG, the background area will appear as black color. So that are the defects which is caused by the faulty algorithms. So that is why usually if you already edit something, especially remove background, the computer will automatic um, ask you or suggest you to save as PNG. If you save as JPEG, it's okay, but might have artifacts, which means the black color, the whole part of background become black color. So when an analog image is digitized, each pixel is represented by a fixed number of bits, which correspond to a certain number of gray level or a color intensity. So in uncompressed format, the digital image require a large number of bits. Actually, this is just to remark why you need to do compressions. Okay, because we don't have sufficient storage, and also we have limited bandwidth. So compression become necessary due to limited communication bandwidth or storage. So these are the primary reason for you to do the compression. So JPEG is lossy, meaning that the compressed image is not quite the same or exactly as you started with, which means most of the information is no longer available if you, although you want to reconstruct it using a very good algorithm, yeah, you just cannot create something from nothing. But in image, actually, we can create something from nothing. Padding is one of the example. Okay. But nonetheless, the after padding, the image is no longer the original one. Okay. So that is meant by here, not quite the same and exactly. So JPEG is designed to exploit the known limitation of human eye. So this is the main purpose of JPEG. Uh, I mean, not the main purpose, but the fundamental of JPEG. Okay, it is to exploit the limitation of a human being. This is the graph, and this is high contrast. Sorry, this is high contrast. This is low contrast. This is low frequency. This is high frequency. So these are the region this is the region where human eye is much more sensitive to. So the JPEG is trying to exploit the human limitation, whereby trying to remove information from this region. Okay, of course not all, but part of it. It relies on three major observations. Useful image contain change slowly across the image. That is unusual for intensity value to vary widely several times in a small region. So we have I mean the JPEG trying to process the image in an 8 times 8 pixel block is that it is less likely for intensity to change significantly across a very small block. 8 times 8 is very small block. 8 times 8 is only 64 pixel in this block, and it is very rare for a normal image to change in terms of intensity violently uh, in just 8 times 8 pixel block. Okay, but if it is a noise, then that is normal. So that is, if that is a noise, after the compression, it might be removed. Okay, it might be, not a must. Okay, so that is the reason the JPEG is choosing 8 times 8. Some might use 16 times 16, but 16 times 16 might cause a higher processing time. So if you have a greater block, so you might have a higher processing time over there. So in order to get the trade-off between the processing time, compression rate, and also image quality, so the JPEG select 8 times 8. So human visual system is much less like this, the loss of very high spatial frequency component than lower frequency component. High spatial frequency component, although these are using spatial frequency, right? So we have spatial domain and frequency domain, right? So spatial frequency, which means like we look on the wall, we can aware that this is a white color wall, right? Okay. Although there might be texture on the wall surface of the wall, right? You know, the unevenness, the texture of the wall, you know, roughness and etc. But it's unlikely for us to observe the texture on the wall rather than the white color of the wall, right? That is because most part of the wall is contributed by the stable intensity across the entire wall. So the same thing applies. So if we have an image and the image is hardly for human eye to ignore the most part of the intensity, which whereby the intensity is changing very stable. You know, like I snap a picture with a green grass and a blue sky. It's very hardly for us to ignore the green color grasses and the blue sky. But in fact, we might not able to identify what type of grass is it. That is the difference of it. So that is why human vision is very less likely to uh, ignore all these high spatial frequency. These are considered as spatial frequency information, which means I would say the low frequency information would be spatial frequency information, which means it's very obvious over there. If you remove all these white color, so you can remain only the texture, and the texture is not ready to be understood by human eye alone. Okay, so human eye simply cannot see much change in color if occur in close proximity. Okay, so which means if you have a change of intensity, but the change of intensity is maybe across 500 times 500 blocks. So for human eyes, this would be um, small change, or like it would be no change at all, because 5 times 500 is quite big lah. Okay, but if you have a changes in terms of 8 times 8, we will see it as a noise. Okay, if it is only affect 1 or 2 pixels, it's hardly for a human eye to see that. Okay, so JPEG is intended for compressing image that will be viewed by human eye rather than to be processed by machine. So this is one of the important loops. JPEG is meant to be viewed by human because the way the JPEG developed the algorithm is to exploit the limitation of human, but not to exploit the limitation of machine, because machine see the image differently from human. Although we try to tailor the machine to see as what we see, because we are trying to use the machine to process the data, right? You know, to capture, to recognize the face, to capture is this people fever, to capture the face recognitions, this and that. So that is how the machine is going to analyze. But the way the machine is analyzed is not like the human analyze. I mean, not like what we can see as a human. So that is why JPEG image is not suitable to be processed by machine. Okay, which means that if you have an image being compressed to become a JPEG extensions. Perhaps for a human being, you're still able to read and tell what is the meaning of this image, but for machine, perhaps after perform the compression, you no longer can get the exact meaning of the image. Give you an example is that if you have an apple image with an apple, after you remove all the high frequency information, you're still able to describe this in an apple. But if you train the deep learning model using the apple image, later on you remove all the information regarding compress it into JPEG and you try to check what the deep learning model going to read this apple how the deep learning model can read this image, the answer might not be an apple. Okay, we do have sort of this test. I think this test is being conducted in Harvard or Oxford. Is that when you have a certain change in pixel, then the deep learning model no longer can tell what it is. But towards human eye, it's the same. For example, you have a baby, not baby, like a flower. You train with a deep learning, and then deep learning say that, oh, this is a flower with a 99% of accuracy. But then later on, you change only one pixel here, and then you input to your deep learning model, it might be telling you this is a baby with a 60% of accuracy, something like that. So this is what we call adversary attack. Okay, I think this adversary attack is being introduced in a conference, I think back to 2012. So it's very new, and this based the concern of using deep learning model, especially in military and also security, especially for airport to identify these people, because this is one of the pixel-based attack. And another case is that when the people, you train these people to recognize, oh, this is Ali. And then later on, this Ali wear a shirt with a special printing here. The special printing is like, color code, like the police color code, different printing here. So it might be recognize this as a cat. So that is this. Nothing changed. Did not put any glasses or whatsoever. Just a barcode, or not a barcode, just a code, color code different change over there. And they test on this code to different items. For example, put this code as a spec for different people, or put it on the bag, this and that. And then later on test out, the result is different. The reason why is that it alters the black box deep learning model to the calculation of deep learning. I'm not sure if you all know, because I think now deep learning is part of the mainstream, especially in image processing. Not only image processing, I believe in all research, it would be a mainstream. So, but basically, I think people are going to use deep learning, using Python, all those available algorithms. But instead, sometimes you can look into, of course, if you want to apply for a specific application is okay. But if you want to know the source of the problems, I would suggest you all to study the mathematical equations, because deep learning has their own mathematical equation. So from the equation that develop the algorithm and develop the layer, this and that. So yeah, that is the reason how people can explore this one. We call it adversary attack. Okay, so JPEG handle only still image. There is a related standard called MPEG for motion picture. But nonetheless, in video compressions, we are actually compress the image, compress the video by referencing this and next frame, or this frame and the frame before it, and also in each frame we perform the compressions. So actually the MPEG or the video compression did use JPEG as well. So JPEG can easily provide 25:5, maybe 50:1. 20:5 to 50:1 compression rate on a full color data. So the algorithm for lossy coding is called DCT-based coding scheme.
DCT. So algebraic comparisons consists of the following step: DCT, quantizations, zigzag ordering, RLE, or DPCM. RLE is for AC. This is for DC. Okay, still can recall the previous one we have. This is the AC coefficient. The rest is sorry. This is the DC coefficient. The rest is AC coefficient. So DPCM, different house code modulation, and is for the DC coefficient, and run length encoding is for AC, and entropy coding. So this will be the entire flow. This will be the entire flow of the. This will be the entire flow of the JPEG compression. So we will start off this Thursday. Okay, just for you all to know, we will have all these steps, which is first of all we perform DCT, we perform quantizations. Quantization is like dividing the table by something else, and perform the zigzag ordering, run length encoding, and difference house code modulation and entropy coding. DCT is on the entire image. Quantization is on the entire image. Entire image would be referring to 8 times 8 line. Because for this flow, we are actually applying on, starting from here onwards, we are talking about 8 times 8 pixel group, which means the same process is applicable. The same process here is applicable to all 8 times 8 pixel group. Okay, so what happened? So I'm not going to talk this for entire, just repeat that. Okay, but for this one, will remain as the entire image. For example, first of all, the input image is being converted to YCBCR, and then subsampling, and then convert to 8 times 8 pixel group, and the rest of it would be based on 8 times 8 pixel group. Okay, so the run length encoding would be for AC, and this DPCM is for DC, and entropy coding would be for after you get both the answer. After you get both the answer, you will need this one. And zigzag ordering is for AC as well. Okay. Any questions? No. Okay. If no, so that's all for today. And this Thursday we have tutorial class. Okay. So we have 1 hour lecture and 1 hour tutorial. And yeah, see you all this Thursday. Bye bye.